We'll now talk about two concepts in functions, inverse and composition, which are easy to define, but I've seen from experience that students often make a lot of mistakes in this topic. Follow the definitions, try not to use your intuition too much, and you will be fine. This is not a hard topic. Let me start with an inverse. The inverse of a function, x and y are just arbitrary sets. The inverse of a function is not the reciprocal. I cannot emphasize this enough. I have seen so many people make this mistake. It has nothing to do with the reciprocal. Then what is the inverse? Is a function, again a function, which is denoted f inverse like that. And I can see why it's tempting to think that it's reciprocal because it's used the same notation. And again, it's very sad that this notation is being used, but it is what it is. And it goes from y to x. Okay, and what does it do? If x goes to y, then f inverse takes y to back to x. So pictorially, I would describe it. If you have f is this, then f inverse just reverses the process. So that's the definition. It just undoes what f is doing. Now, to make sense of this, what should happen? Firstly, everything in the target should be hit. Otherwise, I can't have f inverse defined on the target. So for the domain of f inverse to be y, every value in y must be hit by f. But this is exactly saying that f is onto. If two different inputs go to the same output, then when I try to construct the inverse, I will have a problem because now I will have to figure out where to send this output back to. For f inverse to be well defined, so to have the domain of f inverse, the all of y, I need f to be onto, and for f inverse to be well defined, I need f to be 1 to 1. And this is enough. So from these two things, you can conclude that f has an inverse if and only if f is bijective. This is the only time you can even talk about an inverse. If f is not bijective, then the concept does not even exist. So let me do an example. And this is the first example of inverse you see usually in calculus. So you have f of x equals x squared. Now this function, if I take it from R to R, then it's neither 1 to 1 nor onto. We saw this. But I can shrink the domain and the target and make it 1. So I can say I define it from non-negative reals to non-negative reals. And now this is bijective. And so it has an inverse. And the inverse will swap the target and the domain. In this case, they're both non-negative reals. And what will be the inverse? I want to swap the target and the source. So if I have f of x is equal to y, then I'll get f inverse of y is x. So expanding this out, I will get if x squared is equal to y, then f inverse y is equal to x, and the standard notation for this is square root, and this is denoted. And this is the justification of why the square root function is only defined on non-negative reals and not on all real numbers. And also why it is the case that the square root is always non-negative. Square root of 4 is 2. Square root of 4 is not minus 2, no matter what you do, because the function only is defined on this target and loop. Okay, so that's inverse. There is one more reason why that thing is called inverse, and that brings us to compositions of functions. The idea of composition is, I'll draw it pictorially. If I have a function f from x to y, and I have another function g from y to z, then I can first go from x to y and then from y to z, and that creates a new function for me. And this function is denoted, this is the only part which is really annoying. There's nothing you can do about it. It is annoying. Everybody knows it's annoying, but we are stuck with it. And this is f and then g. So the way I think about this is functions go from right to left. It is what it is. And why is it written like this? Because if I start with a little x in this, so if I start with little x in capital X, then f will send it to f of x, which lives in y. And then g will act on it. So g will send it to g of f of y, which is in z. And so what I'm saying is that g composed with f of x is g of f of, oh, there should have been x there. That is how composition is defined. As long as you draw this picture, you will never make mistake in composition. If you just try to do it in your head, you'll probably get it wrong. So here's an example. I can take the function x squared, and then I can take the function 2x plus 1, and I can ask what is the composition of these two. So I'll start with, let me call this f, and let me call this g, and I want to define f composed with g of x. This is, as I said above, is f. So first I do f, that becomes g of x squared, because f is x squared, and then I do g, that becomes 2x squared plus 1. And if I try to do it the other way, then this is f of g of x, and you get f of 2x plus 1, and that is 2x plus 1 whole square. And if I apply the square formula, I get 4x squared plus 4x plus 1. Note that these two things are very different. So sometimes you can compose functions in both ways. So you can do f composed with g or g composed with f. That is not always the case, but sometimes the target and the domain are the same. So in that case, you can change the order, but changing the order changes the function. Now let me go back to inverse and tell you something very interesting. The reason f inverse is called the inverse of s is because if I have a function f from x to y, suppose this is bijective, and I create its inverse f inverse x, which goes back to x. So inverse swaps the target and the domain. And then I try to compose these two. Then what happens is this result gives me x back. And why is that? Because f of x takes x to y, but then inverse reverses the process, so it takes it back to x. Okay, I can do it the other way as well. I can start with y. I can create the inverse, and then I can apply f back, and I can create the function f inverse composed with f. And now what I see is that f of f inverse y is also y. Same reason, inverse and the function are doing the opposite things. They are reversing each other. And this is the fundamental reason why inverse is called the inverse. So this is a very crucial property of inverse, and why it's useful. It lets you undo the function using composition. So that's compositions and inverses.